Hi everyone, today we're going to continue on with chapter 8. So in chapter 8 we're going to start talking about the hydroboration oxidation reactions. So these hydroboration oxidation reactions are going to be anti-Markovnikov addition. So this is going to be an indirect addition of water. So again, this is going to be a two-step process. Our first step is going to be the hydroboration step. So in the hydroboration step, what happens is we're going to add a borane and a hydrogen across the double bond. And then our second step is going to be the oxidation step. So in the oxidation step, what will happen is we're going to replace the borane with an oxygen in a oxidation process. So if we're looking at this first example, we have this alkene here, we have a two-step process, again indicated by the numbers. And what is going to happen, again, we're going to have that anti-Markovnikov addition. So our hydroxyl or our OH group alcohol is going to be added to the least substituted carbon atom. And our hydrogen will be added to the more substituted. So when we look at the mechanism of this reaction, what is thought to happen is, so we have this borane hydride in solution. This is going to be a Lewis acid base complex. We looked at this, I think it was chapter 1 or 2. So this is going to be in equilibrium with free THF, which is tetrahydrofuran, and borane. So if we look at this, in, again, equilibrium, what happens is we have our borane hydride, we have our THF. So THF is our solvent. So again, THF stands for tetrahydrofuran. So when we look at the borane hydride, what happens is we have this empty p orbital. This is sp2 hybridized. And what happens is it's polarized with the partial negative on the hydrogen atom. So when we look at this hydroboration step, this is going to be a one-step process. So let's look at the mechanism for hydroboration. So again, hydroboration, one-step process. So if we're looking at this alkene here, we're adding borane hydride. What happens is we're going to have syn addition. So remember, syn addition means that we're going to be adding both the borane and the hydrogen in this case to the same face. So I'm just showing you the products right now of that first step, and then I'll walk you through the mechanism. So again, our hydrogen and our BH2 will be adding to the same face. So we have attack from above, which is shown here, and we have attack from behind or underneath. So when we look at the actual mechanism for this, so again, let's look at our alkene. So the BH2 is going to act as your electrophile, and the hydride, so H minus, is going to act as your nucleophile. So we have our BH3 here. So again, this is going to be our partial negative, partial positive, because think electrophile, nucleophile. So we're going to have the formation of this transition state here. So we have our methyl group, and then we're going to have this transition state here. So again, remember, this is a one-step process. Borane is going to add to the double bond in a single step. Borane is going to add to the less hindered or less substituted, and hydrogen is always going to add to the more substituted. So remember, so why hydrogen? Think about it. Why is it going to add to the more substituted? So it's going to be attracted to the greater partial positive charge, and the more substituted carbon atom will be that more greater positive partial charge. So again, syn addition, you can see why it's syn addition, right? Because it's going to be a one-step process. So because it's a one-step process, they either have to add both in front of the page or behind the page. So after this transition state, we're going to form either this product or this product. When we look at oxidation, so for oxidation, we won't be covering the mechanism for this step, but oxidation, again, this is going to be the second step of the reaction. So when we look at the product of that first step, the hydroboration, I'm just going to look at it with one of the products. So when BH2 and hydrogen are both coming out of the page. So hydrogen peroxide and sodium hydroxide are used for this oxidation process. And what will happen is now we are going to just replace our boron right here with a alcohol, so OH. So again, in this oxidation step, that BH2 or boron is going to be replaced by a hydroxyl group. And what's going to happen with stereochemistry is we're going to have retention of the stereochemistry. So we started with a wedge here. The hydroxyl is also going to end with a wedge. Again, this mechanism will not be covered. We don't cover it in Chem 190 in past semesters either, so it's not anything that we're skipping. But it is important that you do know the mechanism for that hydroboration step, and then for the oxidation, you could just replace, again, the boron with a hydroxyl. Let's look at a few examples. So if we look at this first example, so we have this alkene right here. So we have BH3 and THF. So that's our hydroboration. And then we're going to use hydrogen peroxide and sodium hydroxide. So what's going to happen is we're going to have the formation again of two different products. So we're going to have the formation of our hydroxyl, again, is always going to be Markovnikov addition, because again, it's going to go to the least substituted because it's replacing that boron, which is going to be our partial positive. So we have this product plus this product right here. So if you get confused when you're looking and it's hard to rotate the bonds, what I recommend doing is really just looking at the configurations. So going back to chapter 5 with the R and S configurations, this will help you to make sure that you're drawing the correct products. If you have an issue with looking at rotation amongst bonds, model kits may also help you. So we'll call this number 1, we'll call this number 2. So when we rotate the bonds, we have this product here, so SS, and then this one is going to be its enantiomer, so RR. So again, if you have issues with visualizing rotation amongst sigma bonds, I recommend using your model kit or using your knowledge from chapter 5 and looking at the R and S configurations. Let's look at another example. So if we look at something with bulky tert-butyl group, so we have this alkene here. Again, we're going to look at the hydroboration oxidation. So what's going to happen is we're going to have, again, two different products, but this time we're going to have something that is preferred over the other. So we'll have a major product versus a minor product. So we'll have this plus this product. Again, our alcohol is going to add to the least substituted carbon, again, because it's anti-Markovnikov addition and it's syn addition, so they're both going to be in the same phase, so either in front or behind. So when we're looking at product 1 versus product 2, so product 1 would be our major product, product 2 would be our minor product. So the reason that number 1 would be our major product, because you have to think when that BH2 is adding, it's going to add preferentially to the face opposite of that bulky tert-butyl group. So again, in the second step, remember that that OH is just going to replace that boron. And when we think about stereochemistry, we're just going to have retention of that stereochemistry. So there's a couple different types of compounds that we can look at. So we mentioned this in chapter 7 when we were looking at alkenes. We mentioned bridge bicyclic compounds briefly. So bridge bicyclic compounds are going to be another family of compounds where the alkene faces are differential shielded. So they're shielded in different ways. So the most common bridge bicyclic alkene is going to be noroborine. So this is going to look like, so when we're saying bridge, this is our bridge right here. So it's connecting this carbon and this carbon atom. So when we look at this, what this is going to be equal to is we have a hydrogen coming off here. We have a hydrogen coming off here. We'll have our hydrogens here, here. We have two different faces. So we're going to have this face here is called the exophase, and this face here is going to be called the endophase. So the endophase is going to be hindered by hydrogen. So you have to imagine at all of these hydrogens, right? Or all these carbons, we have hydrogens. So when we look at the endophase, this is going to be hindered by those hydrogens. The exophase is going to be more accessible if the bridge is just hydrogens. So again, the bridge is going to be right here. So if those are just hydrogens, then the exo is going to be more accessible. So let's look at a few examples to see what I'm talking about. So let's look at something like this. So again, there's no methyl groups or anything coming off this bridged carbon, so we know that it would just be hydrogens. So that means in this case that our exophase should be more accessible versus our endophase. So that means that the major product here would be our OH is adding at the exophase. So again, this would be exophase. So this would be our major product, and then our minor product in this case would be OH adding in that endophase. So if this is hard to visualize, again, just on your computer screen, I recommend making a kind of think of like a cyclohexane ring, right? And when we looked at chair conformations, and you'll see those interactions of those endo, if you put hydroxyl, for example, in the endo position versus the hydroxyl in the exo position. If we look at a bridge bicyclic compound, so let's look at another example with substituents coming off of the bridge. So if we have something like this, this indicates that we have two methyl groups coming off of that bridge. So again, if we're looking at the hydroboration and then oxidation steps, what's going to happen is the substituents on the bridge, so again, these substituents right here, are going to be pointing towards the alkene hindered approach to the exophase. So what's going to happen is the noroborines are going to be substituted on bridges to usually give the endo as the major product. So whenever you have substituents in this bridge carbon, your endo is going to be your major product. Again, it's just because of the interactions between those methyl groups coming off of the bridge. So our endophase would be, again, this alcohol being added at the endophase, so this would be our major, and this time our minor product would be the hydroxyl being added to that exophase. So exophase. So this would be our minor. So this is going to be always the case when you, again, have substituents in the bridge, on the bridge carbon atom. Your major will be putting the hydroxyl on that endophase. If there's no substituents coming off that bridge carbon atom in a bicyclic compound, then what's going to be favored is the hydroxyl on the exophase, just because it will be more accessible, less interactions. So I'm going to continue on right now with the halogenation of alkenes. So when we're looking at the halogenation of alkenes, what's happening is we're adding X2. So again, X2 is going to be your halogen. So Br2, Cl2 are the most common, and then sometimes you'll see the addition of I2. So again, bromine and chlorine are going to be the most commonly used when we're looking at the halogenation of alkenes. So what's going to happen is if we have this alkene here, we'll react it with bromine. So it's typically done in dichloromethane, which is just your solvent. You guys use this a lot in lab. So you're going to have two different products. You would have this product plus it's an enantiomer, so you'll have this product right here. So what's going to happen is when we look at the mechanism of this, so let's look at Br2. So one of these atoms acts as the electrophile. Oops, sorry about that. Electrophile. And then one develops the negative charge. So again, mechanism is very, very important to help you predict the stereochemistry of the product. So make sure you really do understand the mechanism behind each of these reactions that we're covering. So what's going to happen is we are going to have addition of bromine to one of the carbon atoms, and we're going to form this brominium ion. Kind of the same idea as what we looked at with the mercury. So we have, again, our brominium ion. So our Br minus would be in solution. And again, that halide, so it can be Cl minus, Br minus, I minus, it doesn't matter, is always going to attack the more substituted carbon atom. So again, in this case, we don't have a more substituted, but if we do have a carbon that is more substituted, remember that's going to have a greater positive charge. So that would make sense why that bromine would want to attack at that position. So the bromine is going to, again, always attack at the more substituted carbon if there is one. So we're going to have a backside attack, right? Because this bond here, for example, is going to be breaking as the other bromine is coming in to attack, which would result in the two products that I showed above. So again, if doing the R and S configurations helps you, I recommend doing that. So again, this is going to be always anti-addition. And again, it's going to think of it as an SN2 reaction. So it is SN2-like, where we're going to have that backside attack of whatever the halide ion is, because again, this bond right here would be breaking as that bromine that developed the negative charge is coming in and attacking. Let's look at an example of these reactions. So we'll look at it with chlorine this time. So our alkene in this case is going to be this alkene. We're going to have it in, this time we'll use carbon tetrachloride, which again is just a solvent. So we will have these two products formed. Again, they have to be anti-addition. So one's coming out, one's going in. And then we would have its enantiomer. So again, these would both be major products in this case because we don't really have any bulky substituent that's going to affect which one would be a major product versus a minor product. So we have our Cl2. First, we are going to form that three-membered ring, and we're going to have another chlorine that's going to develop that negative charge. So I'm just going to show this with the wedge. So it's going to be the same exact idea with the dash. So we're forming, again, this three-membered ring. We have our chlorine ion. So what's going to happen is this chlorine ion is going to attack again at that more substituted carbon, since it gives that greater positive partial positive charge. So it's going to come in here and attack. It has to be a backside attack. Again, it has to be a backside attack because it is SN2-like. So as that chlorine bond is breaking, right here, the chlorine is coming in and attacking. And again, the same idea for the other. So we would have kind of just the dash like this, but the Cl minus is still coming in and attacking the more substituted carbon, which would give you this product here. And then we'll look at one other type of reaction today. So we're going to look at the synthesis of halohydrins. So what happens here is you're going to have your X2. So again, bromine or chlorine are going to be your most common. And this is going to be added in the presence of water. So the water is going to always attack the more substituted carbon. So the reason that water will attack the more substituted carbon, again, is because the more substituted carbon is going to have that greater partial positive charge. But it's also because water is going to be, it's more nucleophilic. So when we look at this alkene here, we're going to have the addition of bromine. So we have it in the presence of water this time. So what's going to happen is we're going to have addition of our water molecule or hydroxyl here. Bromine's going to be on the least substituted. So let's look at the mechanism behind this. So what's going to happen is we are going to form, again, this brominium ion or this kind of transition. So we have this right here indicates, just in case you can't tell, it's CH2CH3 group. So what's going to happen is now we have water, right, in solution. So we're going to have an excess of it. And again, it's just going to be more nucleophilic than that Br minus that's in solution. So this is going to come in here and attack the more substituted. So when it attacks the more substituted, we're going to have our water with that oxygen is going to have a positive formal charge, which we don't want. So what's going to happen is our water molecules can deprotonate. So again, water will act as a weak base. It can deprotonate one of those protons. And what we would be left with is our product. So we would have this product here. But we could also have, it's an enantiomer, so we can have this product here. And again, if you're having issues with bond rotation, I recommend doing your R and S configurations to help you see that. So again, we would have both of these products possible. We're going to have anti-addition of the water molecule, again, because that brominium ion is going to form, and then we're going to have that backside attack of our more nucleophilic water molecule. Once we have the attack of our water molecule onto that more substituted carbon, we have to deprotonate one of those protons by using water as our weak base, which will result in most commonly two products, unless, again, you have something that's very bulky in the reaction or in the alkene initially, then you'll have one major product. So again, there's a lot to practice right now. You have your hydroboration oxidation reactions, you have the halogenation of alkenes, and then think about the synthesis of halohydrins. So in the next lecture that we will cover, so this will be the last lecture for chapter 8, this next one that I will do, there are a few things that we chose to eliminate for this semester, and I will mention them as we're working through everything. Again, I'm going to leave them in the partial notes and full notes just in case you're taking Orgo 2 and you would like to look over the material maybe in the summer when you have a little extra time. So I hope everyone's doing well. Please reach out to me with any questions, and I hope you all have a great day.